Well, I would like to welcome everyone to today's webinar. I'm going to go ahead and mute all the lines, so just please hold for one moment.
The conference has been muted.
Okay. Well, again, hello and welcome to today's webinar, Features and Functionalities of Hadoop for Developers, presented by WebAge Solutions, an Avnet Academy partner. I'd like to take a few minutes to go through some housekeeping items. So during today's webinar, everyone's phones will be muted. If you have any questions, please enter them into the chat box and we will address them during the question and answer portion of the webinar. Now I'm going to go ahead and get started. I'd like to introduce our presenter, Brad Brown. Brad, if you want to take it away.
Thank you, Jen. So I'd like to welcome you all to the webinar. In a brief introduction to myself, I am a presenter with WebAge Solutions, an instructor and an independent consultant. My practice revolves around IT strategy, solution architecture, project management, and big data subjects, and training on enterprise architecture, solution architecture, service-oriented architecture, and a number of big data topics as well. And I also do a course at the University of Toronto on the use of big data in enterprises. And WebAge Solutions is an Avnet Academy partner. We provide a broad spectrum of training, both live in person, on site, and over the web, both stock training and customized for a wide variety of purposes. And today what we're going to talk about is the Hadoop ecosystem and its applicability to enterprise development. And I'm going to give you a high-level overview of what Hadoop is, where it came from and its capabilities, and its key components, the Hadoop file system, MapReduce, and a couple of examples of products that are built on Hadoop, like Pig and Hive, that make the platform more accessible and demonstrate the evolution of the platform into a set of tools that's constantly evolving and constantly adding to the capabilities that organizations have to exploit this platform and these capabilities. So Jen, back to you for an overview of Avnet Academy. Oh, sorry, I think Jen, we might have to come back to this at the end. So let me move into an overview of the Hadoop ecosystem. First of all, what is Hadoop? Well, Hadoop is a distributed fault-tolerant computing platform written in Java. So there's a bunch of buzzwords. There's distributed in the sense that it operates over a set of machines, not just a single machine. So it operates in a network. It's fault-tolerant in that it's able to resist failures in individual components in its network. And it's a generalized computing platform in the sense that it's intended for a wide variety of tasks. It's not just a single application. And the fact that it's written in Java means it's available on a wide variety of architectures and wide variety of platforms. The design of Hadoop is modeled after a shared nothing massively parallel processing system. And where this has come from, the meaning of this is it's one mechanism for managing very large-scale parallel computing, in which each of the computing components, each of those individual systems that make up this distributed network, doesn't have to share anything with each other. So there's no shared disk, there's no shared memory. And that has some implications for scalability and design. They go a little bit beyond what we talked about in the introduction. The key implication, though, is it means we can build this solution based on commodity hardware and without needing a lot of specialized architectures. The design behind Hadoop was heavily influenced by ideas that came out of Google. So the Google file system and the MapReduce algorithm were both written up by Google in white papers. And though they were taking ideas that had been used before, they really brought these ideas into the forefront and popularized them and made the core capabilities that were a key part of Google's operations. They were the key underpinning technology that allowed their search engine to work. And by publishing them, they brought those technologies to the point where people could start exploiting them, and Hadoop evolved out of those. It is not directly an implementation of GFS or the Google MapReduce, but is effectively an equivalent taking all the same equivalent concepts. And Hadoop has now become a common platform used for a number of different scenarios, including as a data hub, a place where we bring data in before moving it to other locations, as a data warehouse, so all of the classic capabilities of data warehousing, or as an analytic platform to support large-scale analysis. Hadoop is built up of three main components, and these are the core. There are a number of other components that are optional add-ins, but this is the core of a system that makes up Hadoop. And part of it is the common library. So the Hadoop Common is a library that needs to be installed on every one of the machines to provide the base underpinning platform for Hadoop to operate. The two parts of Hadoop that we're interested in using that are exposed to us as users of the solution are the Hadoop Distributed File System, or HDFS, and MapReduce. And the Hadoop Distributed File System is a file system that operates on large numbers of machines, clusters of machines, which are commodity hardware, oriented towards loading the data once and reading it many times. And we'll get into a little bit about the implications of that more later. And then the other component that we're exposed to as users of Hadoop is MapReduce. And MapReduce is a framework for data processing, which we'll explore again in more depth later. But these two components, storage of data and processing of data, make up the core of what provides Hadoop capabilities. So based on this, we can come up with a simple definition for what Hadoop is. It's a distributed computing framework that provides reliable data storage and a platform for performing analysis. And people have taken this platform and used it for a very large number of applications. So there's a reference here on the page for where you can look at some reference examples of what people are doing with Hadoop in production, many of which are very impressive. The kinds of things that organizations do are things that have to do with dealing with very large-scale information, log and clickstream analysis, web crawling, market analytics, machine learning and data mining, so taking very large sets of data and extracting knowledge from it, or discovering relationships that are in the data but may not be readily apparent. And an increasing use case for Hadoop is data archiving. So using Hadoop as a platform for storing very reliably and at very low cost large amounts of information. And there are a number of systems that have been developed that use Hadoop as a platform, either because they are implemented on top of Hadoop, or they depend on Hadoop as a source of data. And the MapReduce engine is kind of, as a core component of Hadoop, is obviously one of those. And I'll talk a little bit more later about what people do with that. But then there's a whole ecosystem of products that have been added that rely on Hadoop, like Pig, and the Hive data warehouse system, and the Mahout machine learning system, and HBase, a database that's implemented on top of Hadoop, that really extend the capabilities of the base platform. Now, in the context of this webinar, we're really talking about the Hadoop platform itself and a little bit of introduction to some of the add-ons. But I want to emphasize that this is really the foundation of a very large ecosystem of products that goes much beyond just the basic Hadoop platform. It's really revolutionizing a lot of how organizations are doing large-scale computing. Now, this is not to say that Hadoop is the answer for everything, and it's not the one platform that everybody's going to be running to. Hadoop has some limitations. And the first is that it's a very batch-oriented processing system. The very nature of how Hadoop works is essentially batch, and that will become more apparent as we look at how the MapReduce algorithm actually works. So that limits, to some extent, some of the kinds of things that one does with it. An implication of that, an implication of how it works, is that many of the systems that are implemented in Hadoop have a very high latency. What this means is if I ask a query, it may take a little bit of time before the query comes back. Now, Hadoop is oriented towards high throughput, but also high latency operations. So if I have a very large query or a very large operation, I can get tremendous throughput out of the platform, but I may not get instantaneous results. So this is not really oriented toward real-time operations. This is in contrast to platforms like MySQL, Oracle, DB2, kind of traditional relational databases that are really oriented towards very high, very quick response times and real-time response, and support online systems rather than batch. So Hadoop and relational databases largely complement each other. And there's a big gray area between where there's a lot of overlap, and that's a very interesting space right now. And some of that space is trying to be filled by vendors like Cloudera, who are implementing packages on top of Hadoop, like Impala. And Impala is a database implemented on top of Hadoop that's attempting to reduce a lot of the latency issues and broaden the ability of Hadoop-like platforms for more general purpose computing. So with that background, let's look a little bit more into the basic components of Hadoop, starting with Hadoop Distributed File System. The Hadoop Distributed File System is a distributed, scalable, fault-tolerant, portable file system written in Java for the Hadoop framework. So we'll take that sentence apart a little bit. The Hadoop file system is distributed. It operates on multiple computers at once. It's scalable in the sense that we can add more nodes to it, or computers, or servers. And the capabilities of the file system will increase. It's fault-tolerant in the sense that it has capabilities for being resilient to failures within the network, either failures in communications or failures in a particular node. So that it's able to, if I lose a server, the file system will still operate without a lot of degradation. And by the way, this allows us to implement the file system on commodity hardware. So very low-cost computers. And it's also portable in the sense that it doesn't really require much in terms of the machine that it's running on. Any machine that can run a JRE, a Java runtime, can basically participate as a node in an HDFS network, which again reduces my dependence on particular architectures of particular machines. And the way HDFS works is based on a master-slave design. There is a single node, which is the name node, which manages all the metadata. It's the thing that knows about all the files in the file system. And it knows about all the directories and where they're related and their state and whether they've been corrupted and how to repair them if they've been corrupted and so on and so on. This single machine manages the entire cluster. And then there's a number of data nodes, at least three, but generally one has many more than that, that form a cluster of machines that all actually serve the data. So we have this distributed environment where there's a controller and some arbitrary number of machines that are being controlled, all participating to produce this file system. Now, the Hadoop file system design is designed for implementation in large data centers and is so-called rack-aware in the following sense. What it will do is it has knowledge of the topology of the machines that it's implemented on, of the network between them. And it knows things like which machines are, in a network sense, near to each other, generally in the same rack. So that it organizes data such that we try to reduce latency by understanding which machine's data is on, and then issuing a query to the machines closest to the data. This is also used for fault tolerance in the sense that multiple copies of data are kept. And one of those copies is kept in the same rack so that it's available with low latency if there's a failure. And another copy is kept outside of the same rack so that if there's a rack failure, which could occur because maybe a router goes down or some local failure happens, there's an additional level of resilience. So this understanding of the topology of the environment that it's implemented in gives it both higher performance and higher resiliency. And this data reliability, these multiple copies of data, are achieved by taking pieces of files and replicating them in multiple machines, again using this topological knowledge of where machines are, and then doing things like checksumming each part of the file to be able to detect corruption. So we get a very high level of reliability in the sense that I can do things, I can rely on the file system to manage failure. If a file becomes corrupt, the file system will actually be able to detect that fact and it will be able to hide that fact from me as a consumer of the file system. And instead of serving my data from server A, it'll serve it from server B. I, as the user, will never know it. And in the background, HDFS will actually go and repair the file by going off and creating a new copy from the known good copies. So a very, very high level of resilience. Now, by its very nature, HDFS is designed for a particular type of operation. And it's intended to be very efficient at operations that are write once and read many times. And generally, the pattern of operation in HDFS is we load data into HDFS from external sources. So think of a data warehouse or an analytics application where I've got data from a number of different sources, external sources, corporate information, wherever I've happened to have gathered it. I load that into HDFS to make it available for analysis platforms. And then I read it many times. So my analysis engine, my machine learning algorithms are reading the data from HDFS. The thing that's missing from this list, this write once, read many times, the thing that's missing from this list is updates. HDFS is not intended for data which is updated. You don't go and change records. It's possible to do. It's not. It's very inefficient. It's really oriented toward batch operations and large-scale, high-throughput operations. But returning to the discussion of how it's organized, one of the implications of its distributed nature and the fact that it's rack-aware, understands where data is stored, means that data processing, data-intensive jobs can be processed very, very effectively and very efficiently, so very, very high throughput. Because one of the properties I get from distributing data across multiple machines is when I need to perform a read across a very large amount of data, the throughput that I get, the amount of data I can get per second, is not just a single machine and a single disk drive. It's multiple machines cooperating. So again, extremely, extremely high throughput capabilities. Now, the design of HDFS is intended for particular applications and is not intended to be a portable file system. And you know, if you don't know what POSIX is, the implication is you can't just go and mount it. You can't kind of take a machine and say, okay, I'm going to make that HDFS drive my C drive. The HDFS system is essentially enclosed in its own space, and you interact with it through some mechanism. And there's several different mechanisms. There's a shell, the FS shell, which looks like a Unix command prompt and allows you to perform file operations. Then there's a Java API. So Java programs can access data in HDFS using the API, and that's how your MapReduce algorithms work. The MapReduce algorithms written in Java will access data using the API. And then there are other mechanisms. There's a C language wrapper if you want to access it from other places, and there are other mechanisms for doing it. And some examples of what this actually looks like. So here are a few examples of HDFS commands done with the FS prompt. You know, I can say file system ls list recursively. It'll list the files recursively from the root directory in this particular case. The next two examples are showing how we can actually get data in and out of HDFS. So I can upload data to HDFS with a put. I put the file in HDFS. I get it back out again. That's moving it from the file system of the machine that I'm operating on into HDFS, so loading the data. Or I can retrieve data. I can pull the file back out again. And the last example is simply throwing data out. So the message here is the HDFS looks and feels, operates like kind of regular Unix-like file system, but has these very special properties around resilience and throughput. It's very strongly oriented toward a particular set of use cases, and for those use cases, it performs extremely, extremely well. But it's not kind of this general purpose file system that you're going to use to store, you know, the back end of your SQL Server database, for example. Now, the other key component of the Hadoop environment is MapReduce. So MapReduce is a programming model intended for, designed for the processing of very large sets of data. And there are several different ideas about what MapReduce is, all of which are correct. We can think of MapReduce as a programming model, or a way of programming, a pattern might be another way of saying it, of organizing processing. We can equivalently think of it as a parallel processing framework, so a way of performing activities in parallel that gives us the ability to leverage this distributed environment that I've built in Hadoop. I can also think of it as a computational paradigm, a way of organizing computing. It's a kind of equivalent idea. And the last kind of more functional way of thinking about it is as a batch query processor. So I could think of MapReduce as a way of implementing batch queries. Now, the MapReduce as a term was first introduced by Google in the early 2000s. It has been granted a patent, but the mechanism is widely available and part of Hadoop, but actually part of a number of other big data processing platforms. And what the idea behind MapReduce is an implementation of some concepts that have been around in functional programming for a while. In functional programming, every operation in a program is implemented as a function. So now the implications of that are a little bit beyond what we want to talk about, but two of the key things, properties that functions can have, is I can have properties that perform mapping operations and properties that perform reducing operations. And those are kind of descriptors of classes of functions in the functional programming space. And what they do is functions which perform mapping operations take an input, and each element of the input, it maps it or transforms it to something else. But if I give it an array of 10 numbers, the result of a mapping operation is another array of 10 numbers, somehow transformed. A reduce function, functions which fall into this class of reducing functions are ones that take a number of inputs, say my array of 10 numbers, and produce something which is a summary of that or reduction of that. So a simple example of a reducing function is a function which adds the sum of the numbers in an array. So the key observation here, or the key realization that makes the MapReduce algorithm work, is that we can break data processing operations into two phases, a map phase and a reduce phase. And because the map phase is operating on each element of the input individually, the map phase can be run in parallel. So think of my array of 10 numbers. In principle, what I could do is I could implement that in parallel across 10 machines by sending the first element of the array to one machine and the second to the next and the third to the next and so on. Each machine can operate on the element of the array and produce a result independently. So things which are operations in the map phase are inherently parallelizable. And then in the reduce phase, I take the results of the map phase, I take the things that I produced when I was doing these map operations in parallel, and I produce some summary of them. So you should get a feel for the kind of flow of execution that we have in a MapReduce algorithm. The first step, the map step, is highly parallelizable. And I could distribute it across a bunch of nodes, and then I take the results and I summarize them. So what I do is I execute those sequentially. Map first, then reduce, and that produces a final result. Now, I do want to kind of add to this. Often what will be done is data processing steps will not be completed in a single MapReduce operation. Often what I'll do is I'll perform a MapReduce operation as one step in a larger process, and then I'll do another one after that, another one after that. So I chain these things together. The basic concept, though, applies effectively at each step and allows me to have this independence of operation that results in the ability to have an arbitrary level of parallelism. So this plays very well into the architecture that we have in Hadoop, where we have a shared nothing architecture. Because in the map phase, I'm splitting the workload into independent units of work or independent tasks, and I can distribute them across all of the available worker nodes. And because each of those mapping operations operates independently, I don't really have to worry that much about how many nodes they are, where they are, anything like that. I can just kind of fill them up, let them run, and if I run out of nodes, I can just, if I have 1,000 things to do and only 10 nodes, I can just put them through those 10 nodes one after the other until they're all done. And then use the reduce step at the end to kind of summarize the results. Now the implication of this, and the thing that is really dramatic about the results of this for the Hadoop environment, is that it produces a programming model which is linearly scalable. What that means is, if I have an environment with 10 worker nodes, 10 machines, and it does something in a certain amount of time, if I add another 10 nodes to make it 20 nodes, it'll do it in half the amount of time. In other words, the amount of time, the amount of performance is equal to the amount of resources that I add to the environment. Now, contrast that to what happens in most parallel computing systems, where think of something like a multiprocessor machine where I add more and more processors. The challenge in a kind of non-shared nothing environment, in an environment like a multiprocessor, is to keep all those machines and all those nodes in sync. There's overhead to that. So as I add more nodes, the incremental benefit decreases. And in fact, after a certain amount of time, adding more nodes actually makes the entire system slower, which means for most parallel architectures, there's a maximum performance that's possible to be achieved. And Hadoop, or similar shared nothing architectures, don't suffer from that problem. They allow us to scale linearly as large as we want. And to give some sense of scale, people have implemented MapReduce in Hadoop clusters in cloud environments of 10,000 nodes and achieved 10,000-fold scalability, more or less, over a single node. So here's a little bit of a schematic for what this looks like, and this is very abstract. On the upper left, we see a data source, problem data, so that the inputs into the operations that I'm performing. And that data is loaded via the master node, distributed into worker nodes. Each of the worker nodes performs operations and pushes the results of that back into the master, where they're accumulated, summarized together in a reduce step, and that produces the solution data. So the basic concept is we're breaking up the work into chunks. They're performed in these map operations by worker nodes, and then they're summarized together, and the results are collected and the output produced. Now, this is highly schematic. What's actually going on is rather more complicated and more flexible than this, but this gives a good a visual illustration of what's happening. And we can illustrate this in a more kind of programming sense by looking at a JavaScript example. Now, this comes from some JavaScript that's used in a demonstration to illustrate the operations that are happening in MapReduce. So we have this kind of abstract map function and a reduce function. And without going into the details of how this is actually implemented, we can illustrate a little bit more precisely what a map function is and a reduce function are. What's happening in the first step, the map step, is we have this input, which is an array of numbers, 1, 2, 3. And those numbers are being mapped to an operation. In this case, the operation is this function x. And what happens in this function is it's returning x plus x over 10. It's multiplying the number by 1.1. And so the result of the map operation on that input, where the input is 1, 2, 3, is a resulting array 1.1, 2.2, 3.3. Each element of the array was increased by a factor of 10%. Now here's the critical thing that makes it a map operation. The operations on each of the elements of the array are completely independent. And in fact, what I could have done, the way this map function could be implemented, is buried down in its code. It could be taking each of the elements in that input array, shipping them off to another machine, having that machine multiplied by 1.1, and bringing the result back. So that's the fundamental nature of a map operation. Then in the reduce operation, the way this is written here is we're taking the results from the map. See that array, 1.1, 2.2, 3.3, and that's the input into the reduce operation. So what the reduce operation does is I'm thinking about how to explain this verbally. What it's doing is it's taking the array, the input. The net effect is going to be to add up each element in the array. It's a little hard to explain how that actually happens inside this function without going into its implementation. But the net result is it's taking the first element, 1.1, it's adding it to the rest of the array, kind of recursively. So then it says, I'm going to take the rest of the array, 2.2, 3.3, add them together, add to 1.1. I end up with a result 6.6. That operation happens kind of as one operation in one machine. Okay. So what we've illustrated here is something a little bit more precise, how we can perform operations in a parallel fashion and then pull the results together. The actual operations that are being performed here are trivial. We're just multiplying by 1.1 and adding numbers together. But imagine the operations could be very, very sophisticated, very kind of large-scale operations. That's the sort of thing that we actually implement in MapReduce. Now, to make this simpler, one of the common use cases, mechanisms for doing MapReduce operations is to use the so-called streaming interface. What the streaming interface does is it leverages the concept of pipes from Unix. In Unix, there's a common processing paradigm where we have a program which takes input from so-called standard in, performs some operation on it, and sends it to standard out. And this allows us to wire operations together. We can just kind of pipe them together where we're so-called piping the output from one operation into the next. And I can produce a whole chain of operations. And this is a very common thing that's done in Unix scripting for simple processing. This idea has been extended in Hadoop with the streaming MapReduce interface that allows us to write each of the map and the reduce steps in a simpler way. When we use this interface, what it's basically doing is saying the map operations we're going to perform are going to take their input from a standard input. In other words, they're just going to see a stream of input. Think of it as reading a text file. And they're going to process it in some arbitrary fashion, and they're going to produce an output file. They're going to write it to standard out. The Hadoop infrastructure, the Hadoop Common, will handle all of the work of taking the results of that and then piping that into reduce. So we can separate our processing into map and reduce steps without worrying as much about how we actually get the data in and out. It reduces the effort of programming considerably in situations where we can describe our problem space in terms of kind of files that we're reading and writing. Now, making this happen, this is a little bit technical what's actually going on to make this happen, and I raised this because I want to illustrate how relatively easy it is to set up. All we have to do to make this actually happen is we invoke Hadoop. We specify to it that it's to use technically it's the streaming jar. It's a library of functionality. And we give it parameters. We tell it what the input files are, what the outputs to be, and then we tell it what operations are the mapper and reducer. So the modules that are responsible for simply reading from standard in, performing some operation, writing to standard out. So this dramatically simplifies, in many senses, the effort of actually setting up and running MapReduce operations. And It also means that a lot of the operations that I can perform, I can now implement by having this library of mappers and reducers, which I can call on in a configurable way just by changing the command line options. What can I do with this? Well, I can do pretty much anything with it. Here's a simple example. In this simple example, the mapper function is simply the cat utility. So it will concatenate output. It'll concatenate its inputs into output. So what it's doing is it's simply collecting all of its inputs into an output. And the reduce function is the word count. This is the Unix word count operation with the -w option, which means count the number of words. What this will actually do is it will run in parallel a process where an arbitrary set of input files will be concatenated together, and that operation may be done in parallel across a large number of worker machines. And then they'll all be reduced by this reduce operation, which will count the words in them. And essentially what we've implemented is a parallel version of an operation that will count words. Now, again, this is like hello world. This is an example that's so trivial that no one's actually going to do it. You'd never want to run in parallel something that's going to count words, but the principle is very important. In principle, I could do anything in these map and reduce steps, and it's very, very easy using this framework to be able to run them in parallel. So this is an illustration of how powerful the framework is and how relatively easy it is to exploit it. Now this is a kind of an obvious platform for big data analytics. MapReduce as a framework is embedded in the Hadoop system, and yet it still requires work to make it actually do things. So in the previous examples of streaming, I still have to write the mapper and the reducer. And if I'm not using streaming and I'm using kind of more classic old school MapReduce, I have to write the mappers and reducers in Java. And coding in Java, that's kind of an awkward thing to do. If what I really want to do is I want to perform analytics and run queries, and there's a burden on development there that limits the applicability of this solution to certain classes of problems where organizations have certain classes of resources. So we can make things simpler by using packages that sit on top of this, like Big Latin, Hive, Hadoop streaming. Well, streaming we've explored, and it allows us to use platforms other than Java. We're going to talk about Big Latin and Hive later. The message is there are platforms that can be used, that can be leveraged to get the benefits without having all the effort of actually setting this up. The other thing that makes this easier to use is the availability of services and things like Amazon Web Services, who has MapReduce packaged as a service available in the cloud. So there are certain problems which are suitable for solving with MapReduce. And the things that make a problem suitable for solutions being solved by MapReduce are the ability to split the problems into smaller problems, where each of those small problems can be solved independently. So if I can decompose a problem into these independent mapper and reduce operations, in other words, divide and conquer, I can often implement MapReduce as a way of bringing to bear significant computing resources against that problem that would have been very difficult to do otherwise. Now, it should be apparent now that the MapReduce paradigm gives us some certain level of fault tolerance. And where this comes from is the independence of each of these map operations means that if a map operation fails, I simply need to retry it. So something happens in one of my nodes, I don't get a response, I can simply reissue that unit of work. Because it's completely independent, I can be sure that I don't have to do any kind of recovery operations. It's a very different paradigm than I have in solutions where the problem all the parts of the problem have to know something about each other, which happens in grid computing or message passing computing, where I have to actually code into my solution the mechanism for fault tolerance. This also allows me to exploit some significant level of economics in distributed computing by being able to push the amount of work out into independent computing tasks. I can make use of a cluster of machines relatively independent of the size of the problem. If I have more machines, I have more throughput to solve the problem. If I have less machines, it just takes longer. And there are mechanisms inside the Hadoop platform for trying to make sure that work is done on machines that are close to the data to reduce latency and reduce network traffic, et cetera, et cetera. But this core ability means that I can exploit, and what's not mentioned on the slide is because of the nature of the portability of the platform, I can also achieve economics because I can use commodity hardware. So let's take a few moments for a very brief introduction to some of the technologies that sit on top of Hadoop and make the use of Hadoop easier. And one of those is Pig. So Pig is a scripting platform that's intended to be a way of performing MapReduce operations without getting into the details of how these MapReduce operations actually work. And Pig was a Yahoo research project. It has since become an Apache project, and it's one of the platforms that's used to make Hadoop accessible to a broader audience. The way it does that is by implementing a high-level programming language called Pig Latin. You could kind of see that coming, couldn't you? What happens if you write in Pig Latin rather than writing MapReduce programs in Java or writing them directly? So there's a wide set of functions that are available in Pig Latin, kind of basic language constructs. But I can also extend Pig Latin by adding functions that are written in a variety of widely supported languages, including things like Python and Java and JavaScript, and things that are kind of broadly applicable. So it becomes a scripting platform that allows me to do to manage large data operations using a shell called Grunt. So, and again, of course, you can see that coming. I start Grunt, and inside Grunt, I can perform operations. I can issue Pig Latin verbs. So I can say things like load and filter and group. I can load data in. I can specify what operations I want, transformations to happen on the data. I can get the data back out again. I can dump it to the console. I can store it in another file. So for example, here's a brief script. I'm creating a file, file 2, which I'm loading data from a particular data set. And I'm telling it something about the characteristics. Other examples illustrate how we can load data, and I tell it something about the characteristics of it, what the format is, what delimiters. All these are operations that will cause the data to be loaded into the system and available for operations. And the kind of operations that I can do is I can perform group bys and for each, and I can generate results and some things. And the net result of these operations is, in this particular case, what will happen is I have some operations and I'm grouping by ones and twos. So ones and twos are some category of something. And I'm adding up the values in the first column. So the sum of numbers that have ones associated with them happens to be 12. And the sum of numbers that have twos associated with them happens to be 246. Again, trivial for example, but becomes infinitely extensible for large-scale operations. And Pig supports an interface into the HDFS file system, so Pig operates on HDFS files. I won't go into the details. It's essentially the same concept as what we saw in the FS shell before, same idea. So these grunt scripts can be scripts that can perform a large number of operations. And I can essentially build up arbitrarily complex programs. Now, what's the difference between doing this in Pig and doing it in SQL? The primary difference is Pig is a procedural language. You're programming. You're telling it a sequence of operations to perform. SQL is declarative. I tell it what the result is. And the SQL engine is responsible for figuring out how that happens. You could think of this, if you're a database person, as analogous to writing operations in something like PLSQL or Transact SQL. So procedural operations within the database. But it is very much a procedural language, and Pig Latin scripts are really programming rather than database operations. Now that means that there's a difference in use cases. Pig operations will typically be scanning an entire data set, so reading an entire table. This is actually very common amongst in a lot of these big data operations. Many of these big data databases don't have indexes. It's assumed that the analytics that we're performing is sweeping entire tables, what a database person would call a full table scan. And in certain analytics cases, this is exactly what we want to do. But it's very different than what transactional systems would do with a typical relational database. And another key difference is relational databases have ACID properties: atomicity, consistency, isolation, durability. They implement transactions. We don't have any of that when we're using something like Pig. And again, for Pig's use cases, we don't need it. But it's critical to understanding when one or the other should be used. Another example is Hive. So Hive is a data warehouse that's been built on top of Hadoop. And it's intended to be used with large data sets that are sitting in Hadoop and intended to be used to solve warehouse-like problems that typically exceed the capacity of what can be done with traditional relational database problems. And it came out of efforts in Facebook to deal with extremely large data sets that they just weren't able to solve using traditional technologies. So the value of Hive is it provides a SQL-like, SQL-ish interface called HiveQL on top of data that's stored in Hadoop, giving at least a shell of a lot of the benefits of SQL without needing and shielding people from the need to actually program in MapReduce or procedural things like Pig. Now, it doesn't implement full SQL. There are a lot of things it doesn't do. But for kind of query functions, analytics, it performs a lot of the things that people need. It's implemented as a command line interface, so you can sit and interact with it directly. Again, not intended for low latency, not intended for real-time response, but for queries that might come back in minutes, it often works very well. It can also be used in batch mode, particularly for queries that may take considerably longer or things that you want to implement in batch. And some brief examples of what the shell looks like. I could do things like show tables or describe a table. And what you can see from this and this next example are what it looks like is heavily influenced by SQL. Somebody who knows SQL can move into this environment relatively quickly. What you'll also see is it's not SQL. There are things that you're describing here that have no equivalent in SQL, like row format, delimited fields terminated by comma, stored as text file. That's because this table that we're creating, table files, isn't really a special database table. It's actually going to be a flat text file. And that's one of the kind of basic units of work, units of file storage that it operates on. So looks like SQL, has a lot of the advantages and properties of SQL. It's not SQL, it's not a relational database. Okay? Now, we've just scratched the surface of this. I want to take just a moment to talk about some training offerings that are available in partnership with Avnet and WebAge. And 4 of the courses that are available are Hadoop programming, so an in-depth 4-day course on programming Hadoop and actually making real a lot of things that we just touched on here. A 4-day DevOps bootcamp for people who are actually operating environments, building and operating environments, and using them in production environments. Administration training for people who are managing environments and running the environment day to day. And then a data science for solution architects, which is a course that deals with data science issues and the use of Hadoop and use of related products for solution architects. So in summary, what we've done in this fairly high-level overview is look briefly at the Hadoop ecosystem, the value proposition, where it came from, and some of its key characteristics, describe the properties and benefits and also limitations of the Hadoop file system and the MapReduce framework, that form the core of Hadoop, and then a couple of extensions of the Hadoop environment in the pig scripting platform and Hive, two of only many, many platforms that build on top of Hadoop to form the basis of what a lot of technologies are being used today to describe, that are colloquially described as big data platforms. So thank you for your interest, and Jen, I'd like to turn it back to you for Q&A.
Great, thank you. So yeah, actually we got a few questions while you were presenting, so I'm going to go ahead and ask since we only have about 10 minutes left. First question, can HDFS create a RAID between multiple nodes with local attached SSDs?
Well, so good question. Kind of. So you can certainly, so the way HDFS works is an individual node has local attached storage. Now how that storage is implemented is an implementation detail. You could go to a SAN if you really wanted, but it would be a waste of resources. What most people, and so the whole architecture of HDFS is designed on the assumption that you're using direct attached storage and relatively cheap commodity storage. So generally what people do is they take a server and they just attach a whack of disks to it. It's a JBOD, right? Just a bunch of disks. You certainly could use SSD if you wanted. I have never heard of anybody actually doing that simply because of cost. And remember, HDFS will store minimally 3 copies of each file for redundancy. And HDFS is really oriented towards storage of very large files and lots and lots of data. So you're going to make some SSD manufacturer really happy if you try it. Remember also, the purpose of HDFS is not low latency. It's high throughput. And the real advantage of SSD is low latency. So yeah, there's no technical reason why you couldn't do it, but it's kind of a waste of money. It's overkill.
Great. And just a reminder to everybody on the call that we will follow up after this webinar is over with an email that has the recording link in it. So you will have access to this whole presentation post-webinar. I did just get a question about that. Another question I have, Brad, is what does my company need to do to get started to try out Hadoop?
Well, it depends on what you want to do. So the easiest way to get started is if you want to just get a feel for it, there are platforms available where you can simply download a VM and actually work with it. Hortonworks, that's Horton like Horton Here's a Who. Hortonworks is one of the vendors who provides support and kind of enterprise class enhancements for Hadoop platforms. They have an offering where you can simply download a VM and you can actually work with it directly, and it'll work on a laptop. It's very simple and straightforward. If you want to go a little bit beyond that and actually do something useful, you don't need to spend any money to do it. You can do it on Amazon Web Services. So they have all the components to build up a Hadoop cluster in the cloud, and all you're really paying for is compute time. So very, very cheap. If you really want to do it on your own hardware, you need about 6 machines. I'm not sure what the exact minimum is, but I think it's about 6 to build a proper cluster. Now, you can do it on a single machine. You're really only going to get a demonstration. It's not really going to exercise the capabilities. But the key is you can do it with commodity machines. So you could even find some machines that are being decommissioned from a data center and build a little cluster, about 6 machines. All of the software is open source. So you can build this completely without any investment in software costs, even if you want to invest in your own hardware. And then as for resources for learning, probably the best places to go are Hortonworks or Cloudera. Both of those are organizations that offer both free and commercial support for, they have free kind of knowledge resources and commercial support and offerings for people who are doing Hadoop and other related big data initiatives. And they offer excellent sets of things like white papers and training packages and example guides as sources to kind of bootstrap yourself.
Okay. And another question I just got in. You mentioned that Hadoop is portable, but HDFS is not. Can you explain more?
No, I didn't mean that HDFS wasn't portable. When I said Hadoop was portable, the meaning was that it'll operate on, it doesn't have a lot of requirements on the machine it runs on. If the machine runs Java, pretty much that's all you really need. HDFS is portable. I think I remember. Yes, I said HDFS is not a POSIX file system. POSIX is a standard, an interface standard for how machines can talk to a file system. And the implication is HDFS is not something you can mount. So I can't make it into the D drive of a machine. The only way I can talk to it is through an API. So it's internally a file system, but I can't make it a file system for my operating system.
Okay. And so the last question is there a website I can learn more about web crawling?
I'm not sure about web crawling specifically. That's one of the use cases that things like tools like Hadoop support. Not my field, so I'm not sure where I'd want to point you with web crawling specifically. Okay.
And just so everyone knows, there's the contact information here on this page. Feel free to reach out to WebAge with direct questions. And if you have training needs, check out academy.avnet.com. And we will follow up with the recording link after the webinar. Thank you all for attending. We really appreciate it.
Thank you for your time today.
Have a great day.